Okay, class. So we last time ended the class by talking about an application from section 1.6 on how we can use linear algebra to balance a system of equations. And there are several other nice applications in section 1.6 that are very, very nice to look at. And I want to just look at them right from the book. So let's focus here on example 1 from section 1.6. This has to do with economics. This has to do with economics. And the problem says, suppose an economy consists of coal, electric, and steel sectors, and the output of each sector is distributed among various sectors as shown in the table, which I'll show you, where the entries in the column represent the fractional parts of a sector's total output. Now, what this problem is going to deal with is finding what are called equilibrium prices. Okay, equilibrium prices in an economy means that the total outputs of the sectors balance the income of each sector. Okay, so everybody breaks even, basically. You know, any sector in an economy makes money by selling their product, but they also need to buy product in order to make their product. Okay, so this is an economic type model, in this problem here, I'll bring the table. This is the problem right here, or the table, I should say, in example 1, where you have a simple economy. You have a simple economy here, and this is the distribution of output from coal, electric, and steel purchased by coal, electric, and steel. Now, just take a look at that for a moment. Okay, just take a look at that for a moment. And okay, so looking at the columns vertically, what do those numbers, those decimals add up to? If you look at the columns, vertically, 1. That's right, Lewis. They add up to 1. Why do you think that is? Why do you think the vertical columns add up to 1 in this table? The coal, the numbers under coal add up to 1. The decimals, I should say. The numbers under electric, the decimals under electric add up to 1, and the decimals under steel add up to 1. That's right, Lewis. They're proportions or percentages. So the way we read this table is, if you look at like the first row, purchased by coal. Okay, purchased by coal. So coal, the coal industry doesn't purchase any part of itself, but it needs to purchase 40% of electric, okay, and 60% of steel. So for coal production, the coal industry needs to purchase 60% of steel and 40% of electric. Now, why do you think the coal needs to purchase 40% of electric and 60% of steel? To get coal out of the ground, you need steel. You do. You need machines, bulldozers. You see in the picture, thank you, Justin. You see in the picture there, a bulldozer, okay? So, and electric could refer to generators and so forth. If you're gonna go down under the earth, you need You know, you need to power up the elevator, you need to power up the lights in the tunnels and so forth. So yeah, now look at steel. Look at the bottom row. Look at steel. Steel purchases 40% of coal, 50% of electric, and 20% of itself. Okay, so why would steel need to purchase coal, for instance? So there should be some logic. Fuel for machinery, for energy, there you go. Yes, Justin. Yes, Eleanor. So this is how you read this table. And in your web assigned homework for section 1, or MyMathLab homework for section 1.6, you're going to be, which will be due on Friday. You're going to be given, in some cases, you'll be given a paragraph, and based on the paragraph, you have to construct a table like this. But here they give you a table. So, okay. Now, are there any questions so far regarding the table? And incidentally, I guess, you can see they mention here, just to reinforce what we said, the first row of table 1 says that coal receives and pays for 40% of electric output and 60% of steel output. Okay. So now, ultimately, what we want to do is have a system of equations. So in order, for instance, let's focus on coal. In order to make coal's income equal to its expenses, the income for coal has to equal 40% times the expense to electric, and 60% times the expense due to steel. So that first equation comes from the first row in table 1. Similarly, okay, if you look at electric, the income for electric would have to, in order for equilibrium in this economic system to be true, the income for electric would have to equal 60% of the expenses. Hold on now, I want to make sure. Right, it has to equal 60% of the expenses for coal, 10% times the expenses for electric, because electric uses electric, and 20% times the expense for steel. Okay, and so what happens is, and then similarly, you have a similar statement for steel. So what happens is, with these 3 equations, you can create a homogeneous system of equations. Okay, you can create a homogeneous system of equations. Whoops, I always do this. Hold on. Got to learn to use the arrow instead of that. Okay, so are there any questions so far? How we got this system of equations? Who's comfortable so far? All right, Abby, excellent. And Abby, if I may ask, so that second link I sent you, and thanks to Hung and Nema, but that second link I sent you worked. Is that right, Abby? That's the one that worked, that second link in
Yes,
the email
Professor.
I sent? Okay, yes, all right, wonderful. Thank you, thank you. Okay, okay. So, okay, well, so now, man, I keep messing this up. Hold on. So now, we just, you know, set up the system and solve it. And, you know, they do some row operations here. But again, for section 1.6, you may use MATLAB to help you. And if you use MATLAB to help you, you will get the final matrix here. You will get this matrix right here. That's the reduced form, reduced row echelon form of that augmented matrix. Will there be a free variable? Absolutely, there will be. That's right, absolutely. Okay, so let's proceed on then. Let's proceed on to the next page. So the general solution then, you're going to let the steel income or steel output, as they like to call it. One moment here. Just want to. Right. You're going to let the output for steel be free, and then the incomes for coal and energy are as you see here. And so the equilibrium price vector for the economy would be equal to this. So for instance, if you take for instance the I want to say this the right way. Hold on here now, one moment. If you take the income for the steel industry to be 100 million, then the expenses that would be okay, with expenses for coal being 94 million and expenses for energy being 85 million. Okay, and that's an example of a homogeneous system in economics. So now you've seen a second application. First application you learned about was balancing chemical equations, and now you have this second application. All right, is anybody minoring in economics here, or well, who thinks they might? You never know. Okay, well, you never know. You never know. Okay, so now there's a third application also I want to talk about with you. So let me keep going here. We've done the balancing chemical equations application. The third application is an engineering application dealing with network flow. Okay, so systems of linear equations arise naturally when scientists, engineers, or economists study the flow of some quantity through a network. Okay, so they talk, for instance, here about how urban planners and engineers monitor the pattern of flow in a grid of city streets. Okay, how many maybe noticed sometimes when you're, you know, at a red light, like at one intersection, the red light might last longer than a red light at another intersection. How many maybe have noticed that? Absolutely. Yes, Abby. Yes, Stefani. And that's not like, you know, that's not like randomly done. There's studies done that help determine that kind of thing. So in this case, they mention here, and they also mention about calculating current through electrical circuits. That's another thing. And then, but for many networks, the systems of equations involve hundreds or even thousands of variables and equations. Okay, so like for instance, network flow, if you were to look at the network flow in Rockville, you know, there are hundreds and hundreds of intersections with street lights, red lights, you know, the traffic lights, I should say. All right, so what we're going to do is we're going to look at a little example where we have a smaller, like this example 2. This deals with Baltimore streets. Baltimore streets, okay? And the basic assumption of network flow is the total flow into the network equals the total flow out of the network, okay? So in other words, you don't want like jam ups, right? You don't want to have congestion, so you want things to run smoothly, so to speak. So flow is conserved at each junction. Okay, flow is conserved, but I want to be a little bit careful. I mean, what they're basically saying is if you have you know 100 cars that enter an intersection, the 100 cars are going to leave the intersection. That's really what they're saying. But ideally, you want to have a nice flowing network. Okay, and so the problem of network analysis, well, let's just get to the problem here. So here in our example, you have a network, okay, in this figure, okay, a network in this figure that shows traffic flow in vehicles per hour over several one-way streets in downtown Baltimore during a typical early afternoon. Determine the general flow pattern for the network. Okay, so like for instance, if you look at junction A, okay, junction A where you have the intersection here of Calvert Street and Pratt Street. All right, you have 300 vehicles per hour coming into junction A off Pratt Street. How many vehicles per hour are coming into junction A on Calvert Street in this diagram? How many vehicles are coming to that intersection from between Pratt Street and Calvert Street, but coming from Calvert Street? How many are? That's right, Benjamin. 500. 500. That's right. So now leaving that junction A, what variable vehicles per hour are leaving on Pratt Street, leaving junction A? What variable goes with that? So what I'm trying to say is in Pratt Street, you have flow inward and you have flow outward. What variables represent the flow outward on Pratt Street? Good, X1 and X2. That's right. That's right. Good. And it makes sense, right, that we are looking. I want to be a little careful here, but like Pratt Street, is Pratt Street a one-way street in this diagram? Yes. And is Calvert Street a one-way street in this diagram? Yes. So you're looking. That's right. Thank you, Justin. Thank you, Naaman. Thank you, others too. You're looking at the flow in one direction, and you know it doesn't mean that. I want to be a little bit careful. You know, maybe all these streets are one-way streets, but I was thinking if they were two-way streets, you could have a separate network flow pattern for the other direction. But they're just focusing, you know, on going the one direction. But you could have a separate network, a diagram for flowing the other direction, you know, which would, you know, that's fine. That's fine. So, okay. So we have these four junctions. And we need to set up a system of equations. Okay, so, and again, what we want is we want the flow in to match the flow out. So like, for instance, for junction A, the flow of vehicles per hour is 300 plus 500 vehicles. That would then have to equal the flow outward of vehicles, which is x1 plus x2. Okay, that would equal the flow outward. So long it doesn't, I mean, what they're doing is they're giving a little flexibility here in order for this flow, for things to be operating properly. You need, if you 800 cars come in that intersection in an hour, you need to have 800 cars leave that intersection in an hour at Pratt Street Junction, at Junction A there, between Pratt Street and Calvert Street. But it doesn't necessarily mean that you have to, like X1 doesn't have to be 300, X2 doesn't have to be 500. You could have X1 being 200 and X2 being 600, but it has to add up to 800. Okay, so, and then, you know, you have based on the other junctions, you have these remaining equations. Okay, so far, I mean, looking at junctions A, B, C, and D, and looking at the flow in and flow out, are there any questions? On how we get those equations? Wait, did we go blank here on the? Hold on, let me reshare it. Hold on, gotta go back. This happens with this happens. Hold on. Just one moment, class. One moment. We don't want that. Don't need that. Let me make the book. Hold on. Okay. All right, I got to make this visible again. Hold on. Okay, so we're back. It basically, the book, I think it has to do with validating signatures. In other words, every once in a while I need to kind of refresh the book, or else it'll goes out. But can everybody can see the book okay now? Maybe give me a few thumbs up. Okay, great. Thank you, Lewis. Okay, and let me get this off here. Okay, so here are our equations. If there are no questions, now what we have to do is we have to set up a system. But let me ask you this. Is 4 equations going to be enough here for this network flow problem? I mean, how many equations? We'd like 5 equations, right? We'd like here to have 5. That's right. That's right. So they note on the next page, that, well, I want to be a little careful how I say this. Basically, you want to use all the information necessary. And we do have 4 equations with 5 unknown variables. But they also comment that the total flow into the network equals the total flow out of the network, okay, which simplifies to x3 equals 400. So you can see based on the picture here, okay, that you have, like, going out of the network, going, like, leaving the streets, you have, let me see here, hold on. Going into the streets, you have 500 here, that's going in, 300 going in here, 400 going in here, and 100 going in here at South Street. So that's going in, but also going out, you have X3, you have 600, okay, and you have 300 going out. So the flow into the network equals the total flow out of the network. And based on that, you're able to determine that X3 equals 400. Okay, so in other words, I want to phrase this the way I want to phrase it. You can determine what X3 is. That's what they're saying. And so now this is your system of equations. You can use MATLAB. You can enter that in the augmented matrix in MATLAB and reduce it. And so this is your general flow pattern for the network. Okay. And they comment here. Well, first, are there any questions about this procedure? Are we okay with that procedure? Who's feeling comfortable? Okay, Andres is wonderful. Nariana is excellent. Okay. And they make a final comment here that a negative flow in a network corresponds to flow in the opposite direction as shown in the model. Okay, we don't want that. So the streets are one way. So none of the variables can be negative. If you have negative flow, it's like you're going in the opposite direction. Hold on, there was a comment here. Let me see. Eleni asked, why is X3 equal to 400? Okay. Up here has to do with this information here. I didn't check their computation out, but they say that they're saying that hold on here, that the flow inward equals the flow outward. And if you solve that, you're going to have what? You're going to have, let's see here, 800, 1300 equals 900 plus X3. That means X3 has to equal 400. That's where they're getting it from, Eleni. Yeah, this relates to the whole system. That's right. It's like, and you notice they're doing it at just a certain time of the day, in the afternoon. It isn't like whole day, but you know, just in that time in the afternoon. And all right, very good, Eleni, very good. So the restriction is that X5 must be less than or equal to 500 because X4 cannot be negative. So, and incidentally, X1 is 600 minus X5, but if you let X5 be less than or equal to 500, you know, it's a free variable. So you know, if that's true, then X1 would be also positive. Okay, so this is, you know, it's really a very interesting kind of problem because, you know, you might, whoops, hold on, hold on here. Yeah, let me bring this back. So, you have like certainties in terms of coming in and coming out, like the numbers, like coming in, you got 300 from Pratt Street, 500 going from Calvert Street, 400 coming from Lombard Street. But then you have these other numbers, these other variables, and those are allowed to vary. So, like for instance, you might I don't know, want to have a bus stop or something. Maybe X2 there. You want to have a bus stop on Calvert Street somewhere between Pratt and Lombard Street, and the lane and the 2 lanes narrow to 1 or something. So you only let us, so maybe a lot more cars would come through then on Pratt Street than coming through on Calvert Street, because well, of course, people have to go a certain direction, but people might go around. I'm just trying. It's about traffic planning, and or you might want to put a crosswalk or something between Pratt and Lombard Street, and that would maybe slow flow down a little bit, and what kind of flow are you going to allow? It's really, how many think this is really a pretty cool problem? Okay, thank you, Naima. Thank you, Abby. All right, well, great. I'm happy to hear that. Thank you, Haley. All right, well, are there any questions? Before we move on here? All right, I'll stop the recording.